All right, so we made it through binomial distributions. Are we relatively okay with binomial distributions? So I tried to do some of the even ones so that you could get a chance to see sort of how the problems work, but those are relatively standard for the most part too. So.
I have a question on homework stuff.
Right.
Or like just give me a roundabout answer way. I was trying to talk to someone in like Morgan Center and they were like, I'm not even gonna try them because it was David and Kent. And they were like, you didn't take statistics eons ago, but yeah. So number 14 it says P parentheses X is greater than or equal to 6 parentheses, and then N is 7 and P is 0.2. Would you want us to do find the percentage for up to 6 and then use that and take that from 100? Because did you say that the 1 plus the bottom equals 1% anyways, or 1?
Well, what this means, if n is 7, they want to figure out what's the probability that you get 6 or 7 successes. So probably that you're greater than or equal to 6. That's the probability that you're 6 or higher. But how many total trials are you taking with n equal to 7? So that's all you really have to do in that.
So you don't have to do anything before and after them two?
No, because anything that goes above 7 is more than the number of trials you're doing, right?
Okay,
So you don't,
I guess.
yeah, I mean, once you get to n, that's where you always stop, right? So greater than or equal to 6 just means what's the probability that I get 6 corrects or 7 corrects, where my probability is a 0.2 of getting anyone.
I thought that I had to do something less, like you were showing in the notes.
I mean, you could have done,
But
or 1 minus the probability that x equals 0, plus the probability that x equals 1, plus the probability that x equals 2, plus. I mean, you could do that, but which one is easier?
Well, I thought I had to do more, because like you said before, like the one that says a lot greater than or equal to like 20 or something like that.
Well, yeah, but that was when n was 25.
Okay.
So we went from 20 up to 25. So the key to that one is seeing that n is where you cut off.
Okay. So I was really, that was why I was confused.
Does that make sense to everybody? Monroe folks, does this make sense to you? Yes? Ish?
You'll find out when you get the homework.
All right. Okay. So again, when next week on Monday when the homework is due, we will go over some of them. So you will have an opportunity to ask more questions once you have spent a little bit more time on the homework. So 5.3 talks about the Poisson distributions, and it is Poisson, not poison. So say it in a French snooty tone of voice, and you will say it correctly. It's Poisson, right? So you can have, probably there is. I don't know if there should be or shouldn't be, but anyways, Poisson was a French guy, and he's the guy that came up with this methodology for dealing with certain types of probability. So Poisson distributions are timed events where an average number of successes occurs during a known period of time. So the idea would be something along the lines of someone saying, well, normally when I type, 52 words a minute. And then someone says, well, okay, what's the probability that in 1 minute you type 56 words, or more than 56 words, or less than 42 words, or something along those lines, where you know what the average amount is for a certain time, and you are asked to figure out a probability. That's not the exact same question, okay? So that's kind of the way this particular problem works to some degree. The kicker to this is that events have to be independent. In other words, if more than a certain amount of time is going, how you perform on the first timed event should not change what's going to happen in the second timed event. So that the events that are occurring are completely independent of everybody, okay? Independence is sort of a big deal when it comes to statistics, so we'll be sort of focusing on that on a regular basis. All right? So, I never remember this silly formula, but you can look it up. This is the formula for a Poisson distribution. It's going to look weird, so bear with me. And folks, this is an E, like the letter E in the alphabet. And you will notice if you look on your calculator, there is a button there that has a little E on it with an X on the top of it. E to the X power, it's usually very close to the ln button on your calculator because that is the natural logarithm and the exponential function that we often work with.
So what's lambda?
Lambda is a Greek letter, yes, very good. It's the Greek L, if you will. So lambda is the average number of successes that you expect to get in a regular event. And of course, X is the number of successes desired. And again, one of the things that I had to sit through in my graduate school class in statistics was someone proving that this formula is valid and why it makes sense. It was a great proof if you like really, really long algebra problems and calculus problems. Otherwise, it was real pain in the butt. It's a number. It's actually kind of like pi. Yeah, it's like pi except it's E. Again, it's like 2.7 to 2.8, whichever one it is. 718, yeah, 72, okay. So, again, the idea here is that you just need to sort of figure out how to do this one. So, let's actually do a really basic example, right? Let's do that typing example. I type 52 words per minute. What is the probability that I type exactly 50 words in a minute? So again, the reason that this is a Poisson distribution type problem is that you are having some sort of event where you know how much standard or average successes you get in a specific timed event, in this case 52 typed words per minute, and that you're trying to calculate a probability on some sort of a time frame, all right? So I basically want you guys to figure out what is the probability that x equals 50 when lambda equals 52.
How big are these numbers gonna get? Because my calculator doesn't like factorials above 16.
Isn't it fun? Most calculators start to barf once you get factorials rate greater than about 70 or 80, because then there's just, the numbers are too big for it to store in its memory. So some calculators will barf on this, but the fact is that you can just use the formula straight the way it looks, right? So this probability is going to be e to the negative 52 power, e to the negative 52 power times 52 raised to the 50th power, all divided by 50 factorial.
Exclamation point.
Your PRB button.
Oh.
So let's see if you guys, how many of you guys' calculators can actually calculate this number without barfing?
Sorry. It's e raised to the negative lambda.
Yes, to the negative lambda, right? To the negative 52.
You guys are just gonna spit it out, sorry, so I think I have 5.42%.
Sounds like about right. Divided by 50 PRB factorial.
What?
I got like,
For some reason I got 0.05417.
oh,
Yeah.
that's the one.
What, that's what you just said?
Yeah.
I thought it said 50 something, I was
I don't know, I didn't.
Alright, so second E, negative 52. Don't forget to close those parentheses. Up here at 50. Divided by 50 factorial. So you guys should have gotten, if your calculator didn't barf. Did anybody's calculator barf on this one at all?
I'm just not getting the right answer.
What'd you get over there?
I got 0.
You got straight up 0?
Straight up 0.
Ah,
I don't know what I did wrong.
you should have gotten this number. So give it another shot. Make sure that you can get this number. Make sure you know how to use the E to the X button. It's the second LN button
Yeah.
in the upper left-hand corner.
Okay, second,
So if you hit second LN, it gives you E up caret,
right.
and then punch in negative 52. Close those parentheses.
Closed it.
Then
Start
times
parentheses.
52
52.
up caret 50.
Up, caret 50.
Because the up caret's what gets you raised to the power, and then divided by
Divide.
50, and then hit the PRB button,
Oh, see, that's why I didn't do
and grab the exclamation point for the
it.
factorial.
Okay, so that's what that is. I thought that was a power one. I'm like, why would that?
Oh no, that is 50 factorial.
Okay, everything is all right with me.
Did you get it to work?
Yep.
Monroe folks?
Yeah.
Yeah.
Yeah? Okay, cool, good. So the real kicker to this one is just sort of making sure that you can figure out how to punch this in your calculator, because the numbers are a little bit hairy, right? I mean, if the numbers get too big, you may have to slip over into a computer to actually do it, right? If they get, like I said, if X or lambda get over 70, then yeah, then sorry, you're in trouble. Computers can handle it. They can usually get up to about 250 factorial, but even past that, it starts to get a little questionable, depending on whether or not they've got the newest technology in their operating system. All right, so not too bad. All right, so let's try one that's a little bit smaller with numbers, okay? All right, so let's suppose I make a grading mistake. Let's say I make a grading mistake 3 times out of 22 tests. Whatever. if I have to grade 110 tests, what is the probability that I make, well, let's say 7 errors? So this is one that's not necessarily a timed event, but it's the same kind of a feel to the problem, right? Where if there's an average number of things happening during a specific event, this applies the same sort of way, right? So if I normally make 3 errors, or a grading mistake every 3 times out of 22 tests, but now I'm grading 110 tests. What's the average number of times I will make a mistake if I have to grade 110 tests?
15,
Why 15, Ben?
because 5 times 22 is 110.
All right, good. So my lambda on this problem, folks, is 15. Because the average number of mistakes I make is 3 out of 22. 3 out of 22 equals x out of 110. It's a ratio problem. I guess I shouldn't put in x, I should put in lambda. And so you got to multiply 22 by 5 to get to 110, so 3 times 5 gives you 15. So what's the probability that I make 7 errors? E to the negative 7 times 7 to the 15th power. Real quick, I'm going backwards. E to the negative 15. 15 to the 7th power, all over 7 factorial.
I got 1% and change.
Should be pretty small.
Yeah.
Why is that number so small? But why? I mean, what's the conceptual reason behind why that number is so small?
Maybe more tests you grade the less.
I was looking for a mathematical, not a sociological reasoning. Although that's not necessarily a bad answer. The idea is, how many errors do you expect me to make? But given the state of my personal, you know,
At least
3 out of 20.
3 out of 22. If I'm grading 110 tests, how many errors do you expect me to make?
15.
15. So what's the likelihood that I only make 7?
Very little.
Pretty darn small. That's the idea. Okay?
Because you're average.
Yeah, because my average is 15. So if my average is 15, what's the likelihood that I'm like half of that? That, you know, that's pretty rare. And so it is as it works out. All right?
That's a good day for you. And make as many mistakes.
Hopefully this is not a real, you know,
it's extra Scantron, so
Yeah.
don't worry.
hopefully this is not a real rendition of my grading capabilities, but that's the idea. All right? So, let's see. So oh, well,
What do these look like when you graph them?
What do you mean?
Because, like, it's a distribution, right? So you should
Yep.
be able to get some kind of graph out of it.
yes, you should.
Because when I use the when I use the chance of getting 15 errors,
Yep.
then it's like 10%.
Yeah.
So where's,
They all make a bell curve. The idea here is that these numbers will go, so it'll be 10, and then it'll be 9, 7, 4, 3, 2, 1. Well, yeah, it's just a really flat bell curve. So, but all of the distributions are going to be some kind of a bell curve, just so that you know. All right? And it should make sense to you as well, because it's a totally symmetric sort of thing, right? The probability that I make 14 errors is going to be the exact same as the probability as I'm making 16 errors, right? One more than the average versus one less than the average. Those things should be roughly the same. All right? All right, so, not bad. Let's try one from the book and see what the book has to offer for us. What did I assign in 5.3?
4, 8,
6,
12,
10, 14, 18, 4, 8, 12, 14.
4, 8, 12, 14. Did I even assign? I didn't assign 16 or 18 or anything? Oh, that's annoying. You guys should feel ripped off.
no.
All
You know what they say, someone else will.
right, so technically this is number 17 in the book. Pancake House brags that they sell a pancake every 2 minutes. I put it in question mark because I don't believe it. And the question that we have is, what is the probability that no pancakes, if I can spell it, are sold in a 10-minute interval? So they sell a pancake every minute, and we want to know what's the likelihood that they don't sell any for 10 straight minutes. True, when they're closed, 100%. But Pancake House, of course, is an international chain, and it's open all the time, everywhere, period. Come on. Pancake House can't close. We're going to go at 4 in the morning for breakfast. All right, so how am I going to do this first problem, folks? What should I be looking for?
So 0 will be the x.
Yes. I'm looking for a probability that x is equal to 0. What's the other value that you have to tell me? Lambda? Why is lambda 10? Oh, careful.
This is how many should 5, but
Why should it be 5?
every 2 minutes.
Because they sell one pancake every 2 minutes. So if in a 10-minute time span, how many pancakes should they sell? 5.
For some reason, my mind shifted pancake every minute. That's okay.
E to the negative 5 times 5 to the 0th power all over 0 factorial. Folks, what is 0 factorial again? 1. So all you really have to do is do that top thing. And what is 5 to the 0th power?
At risk of admitting that I don't remember parts of college algebra, why is 0 factorial 1?
It's defined that way.
Okay, cool.
0
It's just defined. It's actually defined to be 1. That's a little cheap. Yeah, to some degree. Yeah. it's so that this algebra works. And there really isn't a good explanation for why it is one. 0.006737 or whatever. So percentage-wise, not even 1% chance that this will happen, right? Not bad? So now let's do the twist on it, right? So what is the probability that 3 or less pancakes are sold in a 5-minute interval? So the same stuff that we were talking about in binomial distributions applies to Poisson distributions. You can have less thans, greater thans, more thans, as many as, that sort of a thing.
So this is gonna be like whatever number, C to the whatever number style, where you have to find all of the things in between.
Yes, but you don't have to do the C thing. That's only for binomial. So what do I need to do to figure this one out? First of all, folks, what's lambda? 2.5. 2.5. Because 1 every 2 minutes, that's 2.5 every 5 minutes. And now what am I trying to calculate? 3 or less, right? So I literally want to calculate the probability that x is less than or equal to 3. So what am I going to have to do in order to calculate that, though? I can't do it just by calculating one number. What numbers are less than or equal to 3?
So you're gonna have to do 0, 1, 2, 3.
Yes. X equals 0, plus the probability that x equals 1, plus the probability that x equals 2, plus the probability that x equals 3. So anytime you have less than or greater than, you have to basically add up everything that is less than or greater than.
But you're still gonna do the same math equation from above, but for each one.
Yep, You're still doing the same math for every individual piece of this sum. It's just that the x has to change every time, right? So this, the first one, e to the negative 2.5 times 2.5 to the 0th power, all over 0 factorial, plus e to the negative 2.5 times 2.5 raised to the 1st power, all divided by 1 factorial, etc. down the line. Including 3, e to the negative 2.5 times 2.5 cubed, all over 3 factorial. So it's a little hairy, but it's not impossible. It's not the worst thing in the world to have to do. It'd be nice if that e to the negative 2.5 was a little bit nicer, but. And remember that 0 factorial and 1 factorial are both 1, so those are very easy numbers to calculate. And really, 2 factorial is easy too. It's just 2, right? 6. So let's see if you guys get what I got.
We rounded it a little bit, just because we don't have to do all those long together. And it's still pretty close to that, like, it's still close, but it doesn't have to be exactly what you get or what you understand.
If you write out what you're doing and you say you rounded to 6 digits, I probably let it go a little bit. As long as you're
I
10th,
still got the 75, it was just 8-2 instead of 7.
that's right. So if your 10th place is okay, I would probably say it's all right. So we would both round to 75.8, so that's okay. Again, if you wrote this math sequence out, I'd probably skip it anyways, because this is what's important, is realizing that you have to add all 3 of them up, and that you just kind of repeat the process as you're going.
Same answer. I got 125 was the last three.
If you're right up to 6 digits, you're fine. Again, I didn't keep track of each one of these numbers, I just did this whole thing as one sequence.
I did that
I don't know if they
disgusting mess in parentheses.
Yeah, it's got some parentheses in there.
I just did the first half of it, and then I just switched the 1s and the 2s and stuff like that, like where we put in the 1 or the 2.
Right. It's all it takes.
And I just wrote down the answer quick, like keep
Alright, so not bad. That's the Poisson distribution. It's not overly complicated. It's just a matter of keeping track of what's going on and realizing that, these things, punching them in the calculator can be a little bit hairy. Please note. You are more than welcome to slip into Excel. And just like there is a binomial distribution in Excel, there is also a Poisson distribution in Excel that will calculate these values for you if you ask it to. So if you go into use your statistics. There is a Poisson distribution right there. It's a regular function, just asks you for x, mean, and do you want a cumulative, right? So the example we just did, x was 3, the mean was 2.5, and we said true to the cumulative, and there's the number that we just calculated a second ago. I can make it bigger if you want me to. And it's just a straight Poisson calculation using Excel instead. And honestly, it's just a matter of you using the correct pieces of the calculation inside the function builder, and it'll do it straight up for you. All right. I like the idea of you guys being able to do it both ways. So I would like to think that you could do it with a calculator if you had to, but note that there are faster ways if you wish. Right. So if we wanted to recreate the first prop, the A answer, where we looked at 0, but we only looked at 0 and that was it. Yeah. Is that what we got the first one?
Yep.
Yeah? Okay. So again, if you get a chance, sit down, play around with Excel a little bit. It really can make some of these calculations easier. And if it's easier, that's usually better. And note, folks, that I'm not gonna, there's no in-class test for this. So it's not like you're not going to have access to Excel if you want it, okay? So that's kind of why I want to show it to you, so that you can realize that it's something you can use if you wish. All right.
So does this just break when you try and find out what the chance of getting one thing is with an average of one thing?
No.
Because you take E, raise it to the first, multiply it by, oh, I don't
It's
get
just
it first.
e to the negative first, yeah.
Okay, no, that's fine.
30%. All right. That's Poisson. That's all there is to it, folks. Not bad? No. All right, so the last topic. Oh, this one is much more fun. And yes, it's fun for me.
Oh, not for us.
That was your favorite.
Yeah, that was it for 3. All right, so hypergeometric, this is where you start learning how to play poker, folks. You start using hypergeometric calculations to determine probabilities that certain poker events are going to occur, all right? Well, the idea is it's finding the probability of X successes in N trials where N is the total objects being chosen from, and K is the total successes available. So the idea behind this is that, imagine, if you will, you're getting a 5-card poker hand, and you want to find the probability that you get 2 kings in your hand. A hypergeometric probability calculation is actually how you do it. All right? So, it's sort of a weird, well, I'm not even going to worry about it too terribly much, but you can look these sorts of formulas up, and I always have to look them up because I don't have them memorized, right? I mean, I got it here on a sheet of paper that I've written down so I can keep track of it, just so that you know. All right? So the idea I should give myself enough space. And you guys can copy this formula down from the book. It's in your
Packet thingy.
It's in your packet that you can use to calculate. It's just a bunch of combination stuff. It's very similar to the binomial probability distribution, except it's a little bit different. So it just looks like a bunch of, gobbledygook to some degree. But once we put it into context, hopefully it will start to make a little bit of sense. All right? So, find the probability. I will, there's only 2 L's in will, get exactly 2 kings in a 5-card poker hand. one's capital N and which one's little n? So little n is the number of trials. Capital N is the total number of objects that you're picking from in a particular trial or event. And again, these are, the writing up here is a little obtuse because it has to kind of be generic to handle all of the different cases that may come out. So this is why I do an example where we can kind of see how does it work, all right? So for this probability case right here, all right? First off, what's my x? What am I trying to get? 2 kings. So what's my x? 2. What's my n? How many trials am I doing? How many cards am I getting?
Depends, do you play with jokers? It's a legitimate question.
True.
Because there's 52 with jokers. If you don't use jokers, isn't it just 50?
It's 54 with jokers. 52. 4 times 13. All right, so capital N is the total number of objects that you can choose from. How many cards are there in a deck of cards? 52 cards in a deck of cards. And how many kings are there in your deck?
4. Be that much.
And that's how you build the different numbers in your probability calculation. And now you can just sort of throw them in to see the numbers, right? See how the numbers work out, right? So the first probability is k choose x. 4 kings to choose from. We want to choose 2 of those kings, all right? The next combination is capital N minus k. 52 minus 4. (48), and then it's n minus x. 3. And then we're going to divide that by the total choice probability calculation. Combination of 52 things taken 5 at a time. And this is the sort of thing that poker players actually can calculate on the fly in their head. This is what they're doing. If they really look working off of the probabilities, this is the sort of thing that they're calculating on a regular basis. N minus k. So yeah, up in the formula, that's a capital N and a minus k. Yeah. I was trying to write it neater and I didn't do a good job. Capital N minus k. And if you think about what these numbers represent, the combination of 4 things taken at 2 at a time, this is your number of ways that you can pick 2 kings out of the 4 kings that are in the deck. And the combination of 48 things taken 3 at a time is the probability that you get 3 cards that are not the 4 kings, right? So the number of cards that are not kings is 48. So this is just showing you what's the number of ways that you can get a hand that has 2 kings in it and not a king in the other 3 cards. And then the bottom piece of it is just how many hands can you make that have, from 52 cards, how many 5-card hands can you make? And these are the sort of, like I said, these are the sort of probability calculations that really good poker players can just do, right?
First, I got the 52, the 5-card hand. The top one is the 4 and 2, so that's how many kings, and you're getting 2.
Yep.
Okay.
So this is two of the cards in your hand are a king. This is the number of ways you can get 2 kings out of the 4 kings that are in the hand. And then the key is the next piece is making sure that you don't get any more kings in your hand. So of the 48 other cards, how many other ways can you choose 3 of those to finish building your 5-card hand? And then this is just a straight calculation, right? So it's throw the numbers in and get them, right? So figure out what 4 choose 2 is.
0.039.
Really? I got 9, 8, 8. Or 1, 0, 3, 9, 2, 9, 8, 1, 9.
Choose 3 divided by 52. Choose 5.
4%, is that what you got? So it's basically like a 4% chance that you get a pair of kings when you're throwing a 5-card hand, right? Which is a nice sort of calculation for people to use. So if you're sitting there holding a pair of queens, you're like, well, what's the probability that this person has got a better hand than me, but just slightly better? So if they've got a pair of kings or a pair of aces,
Wait, so that's for the people who are trying to figure out other people's cards so they can see how high they get? Or
yeah,
like
how much they should bet, exactly. And so a lot of times that's what you try and figure out. If there's a, 8% chance that they have a better hand than I do, okay, I will start to say bet, proportionally to that, so that I make that 8% gamble on every bid that I make. Right?
So how would they know they don't make that percent?
Well, they don't know. They're just trying to determine what's the likelihood that they have something better than me.
Oh.
And so based on
By using
that,
their cards?
yeah, by using their own cards and using how likely it is that they get certain hands that will beat them, right?
Gotta really think of how many cards there are though during a poker game, because sometimes it's not only just one deck, it's like 3 or 4.
Well, straight poker plays one deck.
Oh, okay.
I mean, this is not
I was-
blackjack. This is not blackjack, right? Blackjack plays with 5 decks, right? That's totally different. Poker, though, you're playing with one deck, 52 cards. That's all there is to it. Unless you, play house rules or whatever, and you can throw extra cards in while you're going. You ever done that before? If you ever have a poker night some night, one of the rules that you can, so used to be the way we played is that after 10 hands, somebody got to make a new rule. And the new rule was sometimes I'm going to add an extra ace of hearts to the deck. And so now instead of having 52 cards, there were 53, and you could get 5 aces instead of just 4. It was just, it was tripping. It made all of the since I can do a lot of this sort of calculation stuff in my head, it just completely screwed all my calculations up. It was really annoying.
That's when you go away from the calculation and you just read the bullshit on your friend's face.
True.
I mean,
I'm not as good at that as I am at being able to figure out the probabilities. And of course, that's why all my friends would do this to me.
He's the one over there snickering like, oh, I know.
Yeah, it's like, I know what the best bet to make is, but, well. Anyways. All right, so, let's see. Honestly, that's really all there is to the hypergeometric sequence, too. Did I even assign anything in 5-4? Really? Which one did I assign?
2, 4, and 6.
2, 4, and 6? Sweet!
Yeah, 'cause that beats on the
Cheers. My dog and girlfriend used to stop distracting me as I'm on the way home. Especially the dog.
All right, so let's try one of these homework problems from 5.4. So let's see. Well, number 1 we already did. 2, 4, and 6, you said? All right, let's try number 3. Okay, so 12 out of 20 azaleas have pink flowers. The rest have red flowers. Okay. The problem, of course, is that you didn't mark which ones were which when you planted them. So since the flowers haven't bloomed, you're not sure which ones are pink and which ones are red. And so you're just going to sort of pick randomly to determine what you draw, right? So, first question. If you pick 8 flowers randomly, what is the probability six are pink? And the 4 things that you need to figure out are x, little n, capital N, and little k. So that's the nice thing about these sorts of problems is that really you just have to figure out what things you're looking for and then figure out what they are. Okay, so let's start with the easiest one. What's x? That's the 6, yes. It's the successes. It's what you're trying to get. You're trying to get 6 pink flowers. Awesome. What's n? Well, which n am I talking about? Okay, little n. What's little n, folks? 8. The number of events, right? I'm actually picking 8 flowers. The big N is 20 because that's the total number of flowers you're choosing from. And K is 12 because there are 12 out of those 20 are going to be pink. Now it's just a matter whether you can turn the crank on the formula that we built just a second ago, right? N minus K, 8 things taken, N minus that 2 at a time. A neat little thing to notice, folks, is that the numbers all have to add up in the numerator and the denominator. If you add up all the numbers to the left of C in the numerator, they always have to add up to whatever his number is on the left of C at the bottom, right? So 8 and 12 has got to give you 20. 6 and 2 has got to give you 8. It always works that way. So if the numbers don't add up, you know you've got wrong numbers in there somewhere, okay?
Was it? Like 20538? Probably believe it. I got the same. Awesome.
20538, whatever.
22344.
Not bad. Again, the slightly tricky part about that one is sort of getting the whole x, n, and k numbers correctly from the problem that you're working on. Not bad? Well, technically, that is the end of chapter 5.
What I do is
Second part what? Oh, second part? Oh yeah, second part. Since we've got time, we may as well do it.
How's the news previous system?
Alright, so part B of the question. If you choose 5 azaleas, what is the probability none are pink?
So how do you use those things? And then little n and
So big N and little k stay the same, yes. Big N is still 20, little k is still 12, because there's still 20 total azaleas and 12 total pink ones in there. What's X this time? 0 my hero, and what is little n?
What was that just doing?
Note that that first number, combination of 12 things taken 0 at a time, by definition, that's 1. So you don't even really have to worry about that one. So 8 choose 5 divided by the combination of 20 things, choose 5. Oop, that's really unlikely to happen, right? Less than 1%, heck, less than 0.5% of a chance of this happening. And that should make sense, right? Because there's, not that many of them. There's only 8 red ones, and we want to pick all 5 straight red ones. That's unlikely to occur.
Like, you're not picking some things.
Yeah, that's a pretty good bet. Since there's more than half of them being pink, that makes sense. All right. Good. Well, folks, They are not on Blackboard yet, sorry. I can get them on there today. As soon as this class is done, I'll go down there and start photocopying and putting them online. That's all I have, folks. I don't want to start in on chapter 6 yet, so I'm willing to call it a day a little bit sooner than normal.
Don't have to be twice.
Gives you a bigger break than Wednesday. Gives you a bigger break than that.
A little bit.
Yeah, so you got your evening one.
Well, yeah, I have to teach at 6, so for me it doesn't make much of a difference, really.
Well, you're making a difference in the world for us.
Yeah.